Okay, student, this is how you're going to solve for question number 3 for tutorial number 2. Okay, so in this question you're given the feed equal to 100 mole per hour, and you are given the composition of the feed, which is 55 mole percent heptane and 45 mole percent of ethyl benzene. And then you also given the distillate, which contains of 97 mole percent of heptane, and the bottom contain of also 10 mole percent of heptane. And then you are given the condition of the feed. The feed enters the tower partially vaporized, and the components that you have, or the composition that you have, is 40% of your feed consists of liquid and 60% consists of vapor. So you need to answer the question to find your distillate, bottom, minimum reflux ratio, and then the number of stages if you are using total reflux. And then you need to find the theoretical number of tray, given that the reflux ratio is 1.6 multiplied by the minimum reflux ratio. Okay, and then lastly you need to find the actual tray, given that the efficiency is 80%. So these are the equilibrium data given to you, so you need to plot the equilibrium curve. Alright, so with all the information given in the questions, you need to draw the schematic diagram, and then include all the data given to you in the schematic diagram. Okay, so this schematic diagram can make your calculation easier later. Alright, so as I did mention to you, when you are given the condition of the feed, it's related to the feed. So the formula also related to the feed, and then you can see how does it related to the feed. Okay, and then if you are given the information for the distillate, it is related to the reflux ratio. Okay, if you are given the information for the bottom product, you will be given the information related to the gradient of the stripping operating line. This is how you calculate the mole per hour for your distillate, and then the bottom. Okay, so you are to find the two unknowns, where you are also given the information of the feed. Okay, the flow rates of the feed. So you have two unknowns, therefore you need two equations to solve this problem. So one, you get it from the overall mass balance. The next one is, or the second one is from the component mass balance. Okay, so make sure you write the general equation of the overall mass balance and the general equation for the components mass balance. So in this case, this is the component A mass balance. To solve for part B, which is to find the minimum reflux ratio, so you need to use this formula. To use this formula, you need to have the mole fraction of your distillate, and you need to have these coordinates. So this y prime, x prime is called the pinch point. So the pinch point is the point where your operating line intercept with your equilibrium curve. It doesn't matter whether it comes from the EOL, SOL, or QOL. Okay, so at least one of the given operating line will intercept with the equilibrium curve, and that will give you the pinch point. Remember, in the previous information, we are given the condition of the feed. So the condition of the feed will lead you to the Q operating line, and the information is 40% liquid and 60% vapor. So to find the Q operating line, you need to determine the Q value first. So since only 40% liquid, so you have 0.4 multiplied by 1, and vapor you have 0.6 multiplied by 0. So you get the Q value equal to 0.4. With the value of Q equal to 0.4, now you can use the Q operating line equation to substitute the value of Q, and then get the value of the y-intercept of the Q operating line. When you substitute the value of Q equal to 0.4, you're going to get the value of the y-intercept equal to 0.91. So with the y-intercept that you get, now you can draw your Q operating line starting from the XF equal to 0.55, okay, and then you just draw a straight line connecting from this point to the y-intercept. So you get your QOL. From the graph, you can see that the Q operating line intercept with the equilibrium curve. So this point is called pinch point. Okay, from the graph that you have drawn, you can get the pinch point. So the value of pinch point, later you're going to substitute in this particular equation. So you get your minimum reflux ratio equal to about 1.174. So this value is the one that I get from my graph. You might get a little bit different. Now you can calculate the theoretical trace at total reflux. Okay, from my graph, I can get a number of trace at total reflux is about 6 point something, and the theoretical number of trace will be 6 point something minus 1. Okay, to answer question number part D, so you need to know the optimum reflux ratio, where the given relationship is R is equal to 1.6 multiplied by R minimum. So, in the questions, you need to calculate for your reflux ratio first, substitute the value that you get previously, and now you get your reflux ratio equal to 1.878. Alright, from the R that you get, the value of R you get, now you can draw the enriching operating line using the given formula. Okay, from this enriching operating line equation, you can get the y-intercept for the EOL. So once you get the y-intercept of the EOL, you just draw the enriching operating line, okay, starting from x at xd, and then you can see that it will intercept with a QOL. So now your third operating line can be drawn from XB. You just draw and extend the line until it connect the intercept between the QOL and EOL. Now you can draw the stages. Okay, so calculate the stages. Alright. So now you can see, you can calculate the number of trace, and then don't forget to minus 1 to get the theoretical number of trace at the optimum reflux that you have calculated.